Hello again, and welcome to the next video in our Essential Skills for Matrics series. These videos are designed to help you prepare for Paper 1 Physics, not just by learning lots of content, but by mastering the skills involved. I'm Dr. Derek Fish from the University of Zululand, and I'm Director of Unizulu Science Centre. This next video deals with internal resistance. And before this, you should have watched video 4.1 about Ohm's law and circuits. In this video, we're going to be doing a lot of exciting things, looking at some simulations of circuits from PHET, some demonstrations with equipment from Pasco Scientific, and then doing a live experiment in which you will gather the data, draw the graphs, and come to your own conclusions. So I hope you enjoy this video. Before we go to the start, let's go back to the introduction and look from page 3, your contents page. Now, you remember we're dealing with 4 particular skills for physics: graphs, free body diagrams, equations, and multiple choice and ratio questions. This is the last of the graphs videos, and in particular, we're going to be looking at internal resistance experiments because they always give us a graph of voltage against current. Once again, the examiner highlighted in the National Exam Report that interpretation of graphs and graphing skills is a challenge for many learners. So I want to help you with that today. Where does it fit into the syllabus? On page 4, in the electricity and magnetism section, obviously. After the introduction to circuits in grade 10 and 11, in grade 12, we look at internal resistance specifically. And the prescribed experiment is the internal resistance of a battery, looking at current and potential difference. Please remember, grade 10 and 11 work is important. And again, the examiner highlighted the fact that grade 10 and 11 work was poorly understood, and there should be complete mastery of that, especially electric circuits, Ohm's law, power, and energy. Now, as you know, there's 4 main sections in your paper, with mechanics and electricity being the main ones. Internal resistance questions always come up in question 8, which is the electric circuits question. What particular skills do you need? Well, if you go to page 5 and look at the CAP skills, changing the subject of the formula, the example, given here is Ohm's law. That's an important one. You need to understand rate graphs, direct and inverse proportions, but particularly, again, all the graph skills. And you're going to see that those graph skills, especially understanding the mathematical basis of the graphs, will be very important in this section. So let's remind ourselves of the basic graph skills that we need from page 6. On page 6, we remembered there were 3 functions for a graph: rate, relationship, and representation. The internal resistance graphs are relationship graphs between 2 variables, usually voltage and current. Mathematically, they are always linear graphs, they're not curves, but you will see that the graph can have a positive or a negative gradient. What about drawing a graph? On page 6, we introduced you to the TALSIP method. I'm not going to go through this in detail because we did an example in the previous video, and later on in this video, when we do the actual experiment, we'll go through this in great detail. But please just note this on page 6 in your booklets. On page 7, the mathematical basis of graphs. We're dealing with straight line graphs. Straight line graphs have 2 variables: y on the dependent variable on the vertical axis, and x, the independent variable, on the horizontal axis. There are also 2 constants. M is the gradient or slope of the graph, and c is the y-intercept. It's very important not to confuse which are your variables and which are your constants, as we shall see. Now, in video 1.2, the introduction to graphs, we did an exercise with real life graphs. And again, if you haven't watched video 1.2, you should go back and look at that now. We said if you wanted to draw a graph of airtime remaining versus minutes used for a cell phone, you started with an airtime of 200 Rand and calls were charged at 2 Rand per minute, you'd get a graph like this, with your airtime remaining starting from 200 Rand and then declining by 2 Rand every minute. So in the form y = mx plus c, we'd have airtime as the y variable, time as the x variable. The gradient in this case is -2 because you're losing 2 rand per minute. And the y-intercept is just 200 because that was your initial balance. So you could write an equation, airtime equals 200 minus 2 times time. But to arrange it in the same form as y equals mx plus c, we could have a for airtime equals -2, that's the gradient, times time, plus 200 is the y-intercept. Now, this is easy to understand in terms of airtime, but it's no different in terms of internal resistance. And we're going to draw a graph usually of voltage versus current. Please notice the difference from Ohm's law, where current was the dependent variable. Our y-intercept will be the EMF, and our gradient will be the internal resistance. So we'll end up with an equation, the terminal voltage V, the voltage coming out of the battery, equals minus R, the internal resistance, times I for current, plus E, the EMF. Please notice that internal resistance and EMF are constants for a particular battery. They are not going to change, but the voltage and the current will change. So if we compare for linear graphs, here's the basic mathematical form. 2 variables, 2 constants. When we did Ohm's law, our variables were current and voltage, and we had current as the dependent variable. Our gradient was 1 over R, the resistance. And in this case, if Ohm's law is followed and they are directly proportional, then C, our y-intercept, was just 0. Our internal resistance graph looks very different. Please notice the differences. We now have voltage as our dependent variable, current as our independent variable. We start off with the voltage equal to the EMF, and the voltage decreases as the current increases. Now, once again, the examiner made the point in the exam report, learners must be taught how the equations in physics are related to the equations in mathematics. Now, you'll see how important that is if we consider the November 2018 question. I know it's usually question 8, it was question 9 that year. This is the internal resistance question, and it threw everybody out. And the national average for this question was 35%. It was the worst answered question in the whole paper, simply because people did not understand graphs, not because they didn't understand internal resistance. So here's our usual graph in the top corner, V against I. In this case, the examiner graphed resistance R against 1 over current, but even gave that equation in the exam question. So instead of our usual graph, if we take y equals mx plus c, in this case, y was R on the vertical axis, and x was 1 over I. And our gradient now was the EMF, and our y-intercept was minus R. Now, this is what really confused people, because our gradient is usually minus R in this case, but in this particular question, it was EMF. Our y-intercept is usually EMF, and in this case, it was minus R. Now, you're probably very confused by what I'm saying. Don't worry, at the end of this video, we're going to look at this question in detail. The point I want to make is that all that needed to be understood here was the mathematical nature of the graph. And then, in fact, these questions would have been quite easy to answer. But don't worry, we will get there. So, in summary, these are the 3 graphs you're likely to deal with. On the right, we have the mathematical formula, y equals mx plus c. There's Ohm's law, current against voltage, internal resistance, voltage against current, and this special case that came up in November 2019. So you can compare these, but again, they are all the same in terms of the mathematical basis. 2 variables, y and x, and 2 constants. Having finished with Ohm's law, let's continue to page 26 in your books, page 26, and talk about internal resistance. Now, in grade 10, you would have learned that the voltage given out by a battery is called the EMF, or electromotive force, when no current flows. So that's the maximum voltage the battery can give. But we call it the terminal voltage when a current is flowing. And the difference between these two is the fact that every battery has its own internal resistance in addition to the external resistance or the load. So we've got the external resistance R and now an internal resistance in the battery. So our equation V equals IR needs to be adjusted for internal resistance as follows. We now say EMF, the total voltage, is equal to the terminal voltage plus IR, which what we call the lost volts, the voltage drop inside the battery. Now, of course, from Ohm's law, we have V equals IR for the load. So we can also rewrite that as EMF is equal to I times total resistance, internal plus external. Now, please make sure that you know carefully your definition of EMF. Comment from the examiner last year, many candidates were not scientifically correct in defining the EMF of a battery, as keywords were omitted in their definitions. Please, definitions you must get full marks for. In the last module on the photoelectric effect, we put forward this idea that quite often in science, what you put in, is not the same as what you get out. So there's some input, but then there's something that's lost, and then the rest is output. So for example, with Newton's second law, you put in an applied force, but you lose some to the frictional force, and what's left is the resultant force that accelerates the body. With the photoelectric effect, your light energy, HF, is what you put in, but that has to do two things: overcome the work function of the metal, and then the rest goes into the kinetic energy of the photoelectrons. Now, we mentioned looking ahead that with internal resistance, your electromotive force is in a sense the voltage that's put in that's available, but it has to do two things: provide the lost volts with the internal resistance inside the battery, and then the terminal voltage, which is technically what comes out of the battery. So we can write it like this: the electromotive force, that's what's put in, that's what's lost, I times R, and that's what comes out. And it can be rearranged in this form, and that can give us a linear graph. It's important to be able to compare these different systems with this general idea. Let's unpack it a bit further. So there's something input, something lost. Now we know it's not really lost, it's usually converted into heat energy, but that's not useful, plus what is output. So in this case, we have the electromotive forces put in, the lost volts inside the battery are used up, and the terminal voltage comes out. So in equation form, EMF equals V for the internal resistance plus V for the load, which is IR plus V. Now we can rearrange this to get the terminal voltage V is equal to minus R times I plus E. Now the colors should tell us that we're arranging it in the form Y equals mx plus C. Our variables here are terminal voltage and current. EMF and internal resistance are constant for a particular battery. They aren't going to change. They're going to be the constants in the equation, and we're going to have a straight line graph like that with gradient equal to minus R and y-intercept equal to EMF. So once again, comparing from the mathematical form, with electricity, we have two types of straight line graphs. We did Ohm's law. It's a very simple graph, directly proportional through the origin with gradient equal to 1 over R. Now for internal resistance, we have a decreasing voltage, and the gradient is minus small r, which is the internal resistance. Notice as well with these two graphs, the dependent variable is current for Ohm's law, but voltage for internal resistance. It's different. Now, please don't forget to know your data sheets really well. If you turn ahead to page 39, it's the second page of data sheets, and right at the top of the page are the electricity equations. This is what's given for you. You don't need to learn it, but you do need to make sure that you know what each one of these symbols stands for and what units it is measured in. So let's unpack this idea of lost volts a little bit better. We'll do a simulation first, and then we're also going to do an actual experiment. So here is the simulation using PHET's circuit construction kit, which is such a great tool. Now I've set up beforehand a simple parallel circuit. We have a battery. We can change the battery resistance. Let's start with 0 ohms, and we have 2 light bulbs. So if we switch on, the center light bulb will glow, and by switching on this switch, I can actually make both the light bulbs glow. Now, let's measure a few things here, just to show you as well, they're identical light bulbs, and it's a 9-volt battery. Let's connect up a voltmeter because we want to know what is the voltage across the battery. Now notice as soon as I connect it, even with the switches open, it measures 9 volts. So that's the EMF of the battery with no current flowing. If your battery has 0 internal resistance, which isn't really real, but let's just say theoretically you can switch on the switch here and it doesn't make any difference. It's still 9 volts. We can switch on the second switch and still 9 volts is provided by the battery. We're also going to connect up an ammeter just so we can see. And let's put the measuring device actually on the battery here. So when we switch on, we can see the actual current flowing through the battery. When we switch on the second bulb, more current flows through the battery, but because there's no internal resistance, it doesn't affect the voltage. Now let's have a more realistic scenario. Most small batteries like this have an internal resistance of at least 1 ohm. So with a 1 ohm internal resistance, voltage is still 9 volts when no current is flowing. You can see the electrons are not moving. But as soon as I close the switch and the bulb shines, you can see our voltage has dropped to 8.18 volts. And you can see the reason why. We've got a 1 ohm resistor. There's a current of 0.82 amps flowing through, and that gives you a voltage drop of 0.82 volts. 9 volts minus 0.82 equals 8.18 volts. Now I wonder if you can work out what will happen if we close the second switch. Then we'll have 2 bulbs in parallel. The resistance will actually be less, the parallel resistance, than for a single bulb. So what will happen to the current and to the voltage? Will they increase or decrease? And there are often multiple choice questions like this. So why don't you think about it and maybe pause the video at this point. See if you can work out, will the current and voltage increase or decrease? So let's see. If I close that switch, the current obviously increases because now it's flowing through both parallel circuits, but the voltage decreases. And again, it's a very simple calculation. We have a 1 ohm resistor. So IR, 1.5 amps times 1 ohm is 1.5 volts. And that is the voltage drop, which you see here. If we open the switch again, the voltage drop is not so much. And of course, the larger the internal resistance gets with 2 ohms, you can now see the voltage drop is greater with each of these. If your internal resistance becomes too large, like say 5 ohms, and we switch on, you can see the voltage drop is very large and the current actually stays small. Now this is what happens when a battery has gone flat. And of course, it doesn't mean that the battery has literally flattened like that. A lot of people wonder, if a battery is flat, has it lost volts? Has it lost current? Has it lost electrons or charge? And usually what has happened is the internal resistance has increased. And if I keep increasing that internal resistance, you can see the voltage drop becomes larger and larger, and the bulbs get dimmer and dimmer. And that's what happens when a battery goes flat. So I hope that simulation helped you understand the idea of voltage drop or lost volts. Another way of looking at it, though, is with a live experiment where we graph voltage against time. And at that point there, a light bulb was switched on, causing current to flow through the battery. And you can see that drop over there with lost volts. Now we'll do the experiment in a moment using our Pasco sensors. I want to tell you this is very important because this is question 8 in last year's paper. And you can see there's exactly this type of graph showing a voltage drop at a particular time, T1. So doing this experiment, will really help us to understand this idea of voltage drop a lot better. So let's look at this idea of internal resistance, particularly as it applies to batteries. I've got 3 batteries here. I've just labeled them 1, 2, and 3 because their brands are not important. These are the PM9 9-volt batteries. They're very small. Although they may be small, they're not cheap. These cost over 70 Rand each. So we want to know that we're buying a good battery. Now, how do we know that? One of the things we can do is measure the voltage and see, do we get that 9 volts that we were promised? So let's go ahead and measure that voltage. We're also going to record voltage against time, just so we can see whether the voltage is actually stable over time or whether it's changing. So let's have a look. I'm going to connect up the voltmeter to battery number 1. and we will simply record. Now you can see that's really not very promising. It's measuring 2 volts. We can't do much with 2 volts. Clearly, this battery is very old and tired, although it was stable over time. Connecting up battery number 2 and measuring. This looks much better. It's measuring 7.5 volts. And again, it doesn't seem to change over time. And finally, connecting up battery number 3 and measuring. And this is much better. We have 8.7 volts here. So you can see definitely battery number 3 seems to be the best one. Battery number 1 has fallen off, but I think we should get rid of it anyway. So having got rid of battery number 1, which clearly is not much good, let's do a further test on batteries 2 and 3. This time we'll measure the voltage and then connect up this light bulb here. You'll see if it glows, and let's see if the voltage stays the same when there's a current flowing out of the battery. So we'll start with battery number 3. We're going to connect it carefully to our voltmeter here, and we'll start recording. And you can see a nice stable 8.7 volts. Plug in the light bulb, and you can see immediately there is a voltage drop. Unplug the light bulb, and it goes back almost to the first reading. So what you see there is what we call lost volts. As soon as the light bulb was plugged in, current was drawn from the battery, and you have that amount IR, I times the internal resistance, and you can see here on the screen it amounted to about 1.5 volts, and the voltage dropped. As soon as we disconnected the bulb, it went back slowly to the original voltage. So that was number 3. Let's try number 2, which gave us a similar voltage, and let's see if we can rely on this battery. So we'll start recording the voltage. We're getting about 7.5 volts. We plug in the light bulb, and we get absolutely nothing. The light bulb's not glowing. It drops to 0 volts, and it slowly seems to climb back. So the 7.4 volts that this battery claimed was really a bit of a lie. That was the EMF, but it has such a large internal resistance that it has no ability even to light a light bulb. So we'd have to take this number 2 and also throw it in the dustbin, and only battery number 3 is going to be of any use to us. So we can see the startling difference between these batteries, which isn't apparent when we just measure the voltage. And the good battery had just a small voltage drop, whereas the other battery dropped right down to 0, so effectively became useless to us. Just to complete this experiment, let's use our powerful DC power supply and see if we see a voltage drop there. Just to show you the difference here, I've plugged in our DC power supply, and if I record the voltage, you can see it's a nice steady 9.4 volts. I'm going to plug in the light bulb here. You can see the bulb is burning, and you can see it's made absolutely no difference whatsoever to the voltage, whether it's plugged in or out. You can see there's no internal resistance at all from that power supply, and that's why it's so useful for us to use. So at the bottom of page 26, let's do the experiment which is in your booklets. This is an experiment to investigate internal resistance. The circuit shown below is set up, but the resistor is replaced with a variable resistor. That's what that arrow on the symbol indicates. That allows us to change the current flow. So current is going to become our independent variable. Then the terminal voltage is measured with a voltmeter for a number of different currents, and the data will be plotted on the graph on page 27. You can see your table at the bottom of page 26. We're going to take 2 sets of results, one for battery set A and one for battery set B, and you're going to fill in these values. So here's the circuit. In this case, we're not going to use a power supply. In fact, we will use batteries because, as we saw, a power supply doesn't have an internal resistance. And these batteries do have, in fact, they have quite a large and measurable internal resistance. We will use either 3 like this or just 2 connected together to give us different readings. Again, we could measure with an ammeter and voltmeter, and these digital multimeters work very well. This is how the experiment can be set up. Here's the actual experiment seen from above, and here's the circuit diagram. Now you'll see this is our voltmeter. It's connected in parallel across the battery pack. And here our ammeter and our variable resistor, which, as I said, simply looks like the volume control in a radio, are connected in series. So you can see the reading of voltage and the reading of current. Now, for our first reading, we actually disconnect the circuit. So you'll see there's no current flowing at all, and therefore the reading on the voltmeter is simply the EMF. So it's the voltage that comes out of the battery when no current is flowing. Now, as these are each 1.5 volt batteries, 4.5 volts for 3 of them together is what we would expect to see. So as I mentioned, doing it with an ammeter and a voltmeter in this way is absolutely fine. You get good results. But to make sure that you can all see clearly and that I can graph in real time, we're going to use the Pasco voltage current sensor, and it'll be set up like this. So the voltmeter readings will be shown on the digital voltmeter. They'll be recorded in the table, and they will be put on the y-axis of the graph. The ammeter readings, again, will be shown with the digital ammeter, recorded on the table, and put on the x-axis of the graph. And this will enable us to take these readings and draw a graph for internal resistance. So we're going to perform the internal resistance experiment, which is on page 26 in your booklets. Once again, we're going to do a real live experiment. This is not a simulation. We're not using the power supply now, but we're going to use batteries. You can see here I've got 2 batteries in a holder, and I've also got 3 batteries in a holder. And we'll do our first experiment on these 2 batteries, which will be A in your table, and the second experiment on the 3 batteries, which will be B in your table. Once again, we're using the Pasco equipment and the Capstone software. You can see I've got a digital voltmeter, a digital ammeter, a table again. This will be just like the first 2 columns of your table on page 26, and the graph. But I want you to notice what's different. You see that voltage is now the dependent variable, and current is the independent variable. In this case, we will be directly changing the current. Now, how do we directly change the current? Well, I have this thing here. This is a variable resistor. It's like the volume control on a radio or the temperature control for a plate on the stove. And by turning the knob, I can change the resistance in the circuit, which changes the current that is drawn from the battery. Once again, we take our first reading with the circuit disconnected. So we are effectively measuring the EMF on open circuit. So if we switch our system on, you can see we have a reading of 2.82 volts for 2 batteries. I'm going to keep that sample. That is our EMF reading. Now I want you to see what happens when I connect up the ammeter. You'll see the current reading is 0. I plug in the ammeter. Immediately we get a current reading, and immediately you can see that the voltage has dropped. It was 2.82, it's now dropped to 2.38. Give it time to stabilize, and then we keep that second reading. Now the experiment is very simple to perform. All I do is turn the variable resistor, which increases the current in the circuit, and you can see that as the current increases, the voltage decreases. Now, of course, that's because of the lost volts, as I explained, and the internal resistance in the battery is causing heat loss. So there is our third reading, and the current is 0.3 amps. The voltage has dropped to 2.16. Let's again turn the current up by decreasing the resistor. Give it some time to stabilize. And I can take the fourth reading. And then finally, we'll just take one more reading, because you've got space for 5 readings on your page at 0.68 amps, 1.65 volts. Let's see if we can squeeze out a last reading. Turn the current up as far as we can. Let's see if we can, that's about as far as we're going to get. 0.77 amperes and 1.53 volts. And we'll stop over there. Now you can see a very interesting graph. We can maybe just make it a little bit taller there. But you can see that from the initial EMF, which was 2.82, and when the current was 0, you can see the voltage is systematically dropping. And of course, that's what we expect because of the internal resistance in these batteries. The fact that we have 2 batteries in series here, of course, means that the internal resistances are actually added up. So it's actually slightly worse in this case. Now we're going to try it with the 3 batteries. So you'll see that I've now put the 3 Duracell batteries in. And as expected with 3 batteries, our EMF is higher. With 0 volts in the circuit, it's 3.92, sorry, with 0 amps in the circuit, it's 3.92 volts. Now, once again, I want you to observe what happens when I connect up the ammeter. I'm plugging it in there. Immediately, you can see we get a reading on the ammeter of 0.25 amps, and the voltage, as we expected, has dropped to 3.27 volts. And again, we'll proceed in exactly the same way, just changing the variable resistor to increase the current in the circuit. We don't have to stop in the same places as before, allowing the voltage to stabilize, and we take a reading. Our 4th reading, we let some more current flow. Again, you can see the voltage is dropping systematically. Let's take a 5th reading with some more current flowing, current of 0.62 amps. Voltage has dropped to 2.32. And then let's take one last reading with a large current flowing, 0.74 amps, and our voltage has dropped to 2.02 volts. So there you can see very nicely, remember that this blue run over here was for the 3 batteries, and the first run at the bottom, now the dark blue, was for the 2 batteries. With 2 batteries, we can definitely see a lower EMF, but we suspect that the internal resistance is less because it's not sloping as steeply. With the 3 batteries, we can definitely see a higher EMF. Our table shows us that was 3.92 volts, but the internal resistance seems to be greater because we have 3 batteries in series adding their internal resistances. So again, having finished taking our readings, let's enlarge the graph and have a little bit of a closer look at run number 2. So here's run number 2, was for the 3 batteries. Again, we can ask this great software to give us a linear fit, and then we can have a look. Now, what's very nice about the internal resistance experiment is that the gradient and the y-intercept have real meaning. So it gives us a y-intercept of 3.91, and so that is the EMF as taken from the best fit curve. Now notice our regression coefficient R is -1. That's simply because it's sloping downhill. It's a negative gradient, but minus 1.00 tells us that we have almost perfect results. Gradient of the line is minus 2.57, and that is just minus R. So the internal resistance for that set of 3 batteries is 2.57 ohms. We can read that directly from there. Let's look at the other graph, run number 1. And again, let's ask for a linear best fit. And we can see it wasn't quite as accurate a straight line, but still the regression coefficient is very good, minus 0.99. In this case, we can see 2.71 over there as our EMF, and we can see an M value, the gradient, of minus 1.59 ohms. So I think you'd agree that what's come out of this experiment very nicely is these 2 graphs showing us the effect of internal resistance. Run number 1, the one at the bottom, was for the 2 batteries, so we see a lower EMF, but also the lower gradient tells us the internal resistance is not as large. Run number 2 at the top for the 3 batteries gives us a higher EMF, 3.91, but also a steeper gradient indicating a greater internal resistance. So you can see because of that, by the time about 0.8 amps is flowing, actually these 2 sets of batteries are providing about the same terminal voltage. So let's make sure that you've got all the data from the internal resistance experiment. First of all, run number 1. This was our data we called A in your table. And if you can fill all of those in and just make sure that you've got those for run number 1, that was for the 2 batteries. Run number 2 was for the 3 batteries. Again, these are the data points that we recorded, but I've put them all together here in a large table, and the teacher can pause the video here and just make sure everyone has all the data from A and from B. And all of this should be entered in your table on page 26. Now on page 27, we're going to take this data and we're going to graph it. So just like we did for Ohm's law, we're going to use our acronym TELSIP to remember all the important parts of the graph. So first of all, T. T is for title. We write an appropriate title. And in this case, it's not current versus voltage like for Ohm's law, but voltage versus current, because voltage is now our dependent variable and current is independent. Please notice how this has changed from the Ohm's law experiment. We've labeled our axes with appropriate units, and now we want to look at the scale. For the scale, of course, we're going to need the data points, so we have them here. So let's have a look carefully at this now, because we need to choose the correct scale. Once again, the graph paper has 11 blocks on each axis. So on the x-axis, we have current, and current ranges from 0 to 0.77. That's the largest value of the two. So we can use 8 blocks, and one large block should equal 0.1 amps. And that's what current is going to look like, going up to a maximum of 0.8. Voltage on the y-axis, it ranges from a low of 0 to a high of 3.92. We do need to go all the way down to 0. So one large block should equal 0.5 volts. So again, we have that scale for voltage there. Now, what about intervals? Within a large block, there are 5 small blocks. On the x-axis, one large block equals 0.1 amps from there. So we divide that by 5, and each of these small blocks is 0.02. On the y-axis, one large block equals 0.5 volts from there. Divide by 5, and each small block is 0.1, which makes it very easy. Now, at this stage, you need to take this and plot your data onto the table, making sure you get the x and y coordinates in the right order. You're going to get 2 sets of points, one for the A readings and one for the B readings. And then I'd like you to plot 2 best fit lines and calculate intercepts and gradients. So please pause the video and plot those graphs, and don't proceed before you have plotted them. So let's see what these graphs would have looked like. And again, it's going to be difficult for you to check your data points from the screen, but this is what they should look like. First of all, starting with the A readings for 2 batteries, we have our first reading not at 0 like for Ohm's law, but this is your EMF reading, that when the current is equal to 0, our voltage is 2.82, which will turn out to be the EMF for 2 batteries. As they are 1.5 volt batteries, we would expect something close to 3. Next point, 0.17 amps and 2.38 volts. These are much more difficult to plot than for Ohm's law, because they don't lie exactly on the lines. So you need to carefully find the correct points of interception for these 6 data points. So you can see it's pretty much a straight line, although not perfectly so. Now, moving on to, in orange, for the 3 batteries, our B readings, when the current was 0, our voltage was 3.92. That's the EMF, much higher because of 3 batteries. 3 batteries equals 4.5 volts, so we would expect something around there. Again, we can see these lie in a nice straight line. Now, going to the conclusion, which we find at the bottom of page 26. First of all, we need to try to draw our best fit straight lines. Remember again, don't play join the dots. Don't simply join the first and the last dot. Try to find a line which lies closest to all the data points. So in green, for the 2 batteries, our A set of readings, from the intercept, we calculate that the battery's EMF was 2.71 volts. Now notice we don't simply take our first point, but we take the intercept from our best fit straight line. From the gradient, we calculate that the battery's internal resistance was 1.59. If you do a calculation on the gradient of that line. For the 3 batteries, there's our best fit line. Again, starting with the intercept, we calculated the EMF was 3.91 volts. And from the gradient, 2.57 ohms. Now, of course, I got these figures from our actual experiment when we did the analysis by the computer. For the A readings on 2 batteries, gradient of minus 1.59, that's the internal resistance of the battery, and 2.71, the y-intercept gives us the EMF. we can see for B with 3 batteries, we actually have a larger EMF. We also have a larger internal resistance. Now, of course, it can mean the individual batteries had a large internal resistance, but it can also simply mean that because you had 3 batteries and they were in series, we were adding up those internal resistances. So let's finish off this video on electricity by looking at the internal resistance exam questions on pages 28 to 30. Now, as always, there are 3 questions here which total 26 marks. So if you haven't tried them, you should pause or stop the video here for 26 minutes while you try to complete these questions. It's very important to try them for yourself before proceeding. So please do that before we mark them and give you the answers. So we'll start with the question on page 28 from November 2014. What was interesting about this question is this graph paper was given to you in your answer sheets, and you were required to actually plot an accurate graph, which is one of the graph skills we did mention in the very first video. You were given the data from the experiment. It's the usual internal resistance experiment. State one factor which must be kept constant. That's always temperature, but they often ask that. But you're supposed to use this information to plot the points and draw a line of best fit on that answer sheet and give it in with your exam. So let's have a look. Here was 8.1.2, and that's where the points are plotted. Now again, you'll have to look and make sure you've plotted them carefully. Voltmeter readings are easy because they're on the line, 6, 5, 4, 3, 2, and so on. Ammeter readings are not quite so easy. Let's look at the first one. For 6 volts, you have an ammeter reading of 0.14 amperes. Now, if that's 0.2, then every small block counts 0.02. So 7 small blocks gives you 0.14. And then you draw the line of best fit. Again, don't play join the dots. Draw the line that fits best through those various different points there. 8.1.3, calculate the EMF of the battery. Well, that's very easy because EMF is just the y-intercept. And again, you need to be able to count the blocks carefully and see that that's actually 7.2 volts. 8.1.4, calculate the internal resistance. Well, from the equation, we can see that the gradient for the graph is just equal to minus the internal resistance. So internal resistance equals minus the gradient. Delta y over delta x, and we've just used the big triangle here. You can see the y, the voltage is going from 7.2, the answer we got there, down to 0, and the current is going from 0.8 to 0. So do that calculation, and we get an internal resistance equal to 9 ohms. 2018. The question that confounded everybody. National average for this question, only 35%. Because they took the usual internal resistance graph we're used to and changed it completely. Now, as I've said before, you still need to look at it in mathematical terms, y equals mx plus c. And in this case, this equation was given to you in the exam. Resistance equals E, that's your gradient, EMF, times 1 over I, the current, that's your x variable, plus minus R. And so it's a little bit different in that your gradient is usually minus R, but in this case it's E. And your y-intercept is usually EMF, like in the usual graph, but here it is minus R. Once you've taken note of that, though, it's not a difficult question. So just answering, remembering again that these have changed place. And please try to do better than the 33% national average for these 2 questions. Now, once again, just summarizing, that's your standard mathematical form for a linear equation and a straight line graph. That's Ohm's law, your simple graph, plotting I against V. Internal resistance, V against I. And this was in the November 2019 exam. You can see how it's been changed around and how the gradient and y-intercept have been swapped. So hopefully this summary is a useful way of looking at it for you. Getting to the answers, 9.1, as always, asked what variable must be kept constant, and that is temperature. 9.2.1, write down the internal resistance of the cell. Well, that is minus R, the y-intercept. So don't write minus 3 ohms. How do we know it's 3? Well, 10 small blocks equals 5. So 6 small blocks equals 3. That we learned using the Talsop method. And then 922, calculate the EMF. That's just the gradient. So where do we get these numbers from? Well, we're going to calculate gradient with that green vertical height over that red horizontal distance. Now that point there, which is given on the graph, you can see clearly the x value is 1.5. The y value, halfway between 5 and 10, is 7.5. This value here is where minus r is. So point x equals 0, y equals minus 3. So the height is going from 7.5 to minus 3, actually going 10.5, whereas the base is going from 1.5 to 0, and that'll give you an answer of 7 volts. And finally, the November 2019 example, a different type of graph again. So this is interesting because we had 3 graphs and all of them different, which is why I chose these questions. This is kind of like a rate graph because we have time, but it's not really. I've called it a step graph, and I'll explain that in a moment. So when the switch is closed, the voltage drops from 13 down to 10.5. And you would have seen that both in the simulation and in the experiment which we did earlier. So let's try to answer the questions. They're not too difficult. 8.1 is very easy. Define the term EMF. That's a definition for you to learn. 8.2, write down the EMF. EMF is simply the voltage before the switch is closed, before the current flows. 8.3, after the switch is closed. Now please, because it's after, we must use 10.5 for the terminal voltage, not 13 anymore. Calculate the current through R. Well, current I is just V over R, which is 10.5 over 5.6 ohms for the resistor that was given in the question, equals 1.88 amps. 832, calculate the power dissipated in the resistor. There's 3 equations you can use. I think the simplest is power equals voltage times current. 10.5 times 1.88 amps. That gives you 19.74 watts. Finally, calculate the internal resistance of the battery. Notice now we're doing this by calculation and not from the graph. Well, of course, the internal resistance is what causes those lost volts. So the simplest way is to say the internal resistance, small r, is V internal divided by I, which is equal to 13 minus 10.5, that's the lost volts, divided by the current 1.88, equals 1.33 ohms. Apologies, of course, that R should be a small r. So as I said, this is what we might call a step graph, and these come up quite often. You will see June 2019 had a Doppler graph, which was a step graph. June 2015 had a momentum graph, which was stepped. So it's not really a rate graph, but at the time T1, something happens. With the momentum graph, that's where the collision happens. With the Doppler graph, that's where the vehicle making a noise passes the listener. And with the internal resistance graph, that's where the switch was actually closed. So just pay attention to these, and this is a type of graph you might get in these examples. So I hope that those 3 exam questions were useful to you. We chose those 3 particularly because they all involved graphs, but they all involved different graphs. And if you can master those 3, you should be fine with any internal resistance graph. Of course, question 8 doesn't have to involve graphs and sometimes just involves circuits. So we're going to look at an extra exam example, the November 2020 question 8, to give you a little bit more practice. This is not in your books, so just pay attention to the screen. So here is question 8 from the November 2020 final matric exam, paper 1. It's not in your book, so just pay attention on the screen. So you've got a circuit that's set up. In the external circuit, you have 1 resistor in series and 2 in parallel. We have an ammeter and a voltmeter, a switch that can be closed. And then this is an expanded view of the battery, which has a certain EMF, but has its own internal resistance of 0.5 ohms. Notice that because you'll need it quite a lot. 8.1, define the term EMF of the battery. That is just basic recall, and you can learn that. Then there's various questions and calculations on what happens when the switch is closed, because you're told the reading on the voltmeter decreases by 1.5 volts when the switch S is closed. Now, as we're at the end of this video, you've seen lots of demonstrations and experiments which show that when the switch is open, you read the EMF, which is higher. When it's closed, you read the terminal voltage. So let's look at question 8.2. Give a reason why the voltmeter reading decreases. And we just need to say the internal resistance of the battery causes a voltage drop, and it's equal to I small r, as we'll see in the next question, when a current flows. So the switch is closed, the current flows, and we get a voltage drop. 8.3, calculate the following, the reading on the ammeter. Well, all we need to know for now is that the voltmeter decreases by 1.5 volts, because that voltage drop is equal to the current times the internal resistance. So we have current equals 1.5 that we got from there, divided by 0.5, that's ohms, the internal resistance, and that gives you a current of 3 amps flowing through the external circuit, obviously not through the parallel branches, but through the main external circuit, and importantly, through the battery as well. 8.3.2, calculate the total external resistance of the circuit. This is really grade 10 work, just adding 2 parallel and 1 series resistor. I'm not going to go through all the detail, but you can calculate that the parallel resistance, equivalent resistance, is 9.375. Remember, the equivalent parallel resistance will always be smaller than the smallest resistance. So you can look at that and say that's probably correct. If you get an answer of 20, you can know you've done something wrong. Now we add that 9.375 ohms to the 4 ohms that it's in series with, and we get a total external resistance of 13.375 ohms. Now we expect that these answers are going to be used in the next one. Calculate the EMF of the battery, 8.3.3, and the equation given on your equation sheets is EMF is equal to I, the current, times the total resistance, external big R plus internal small r. So the current is 3 amps. We got that from 831. The external resistance is 13.375 ohms. We got that from 832. And the 0.5 is what we were given. Do the calculation and you get an EMF of 41.625 volts. So not too difficult. One just has to remember the calculations. And you saw how important it was to be able to do the equivalent resistance calculation from your grade 10 work. 8.4, a learner says the current through R3 is larger than the current through R2. Is this correct? This has nothing to do with internal resistance, but yes, it is correct. The voltage is the same for each of the parallel branches. The current is inversely proportional to resistance. In other words, the bigger resistor R2 will have a smaller current, and the smaller resistor R3 will have a larger current going through it. Finally, the 4 ohm resistor is now removed from the circuit. How will this affect the EMF of the battery? Well, this is quite tricky because the answer is actually it remains the same. Now, you weren't asked to give an explanation, but just to help you, I have given one here. EMF is a constant for a battery, EMF and internal resistance. Remember, I stressed this with the graphs. So it's unaffected by external resistance or current flowing. So important to remember that, please. So that is the end of this video 4.2 on internal resistance. I hope it's been useful, and this is the end of our videos on applications of graphs. I hope you will see that a graph is the result of an experiment. It's not just something that exists in the abstract. We take the readings, in this case it was voltage and current that we recorded from our instruments, plot them on the graph, and draw conclusions from the gradient and the y-intercept of the graph. I hope this was useful. As always, please keep watching for an inspiring interview. So I'm glad to be able to speak to Professor Kunene, who's the Dean of the Faculty of Science and Agriculture at the University of Zululand, which of course has supported the Unizulu Science Centre for all the 34 years it's been around. Thanks, Prof. Kunene. Can you tell us a little bit about yourself and just where you come from and what you studied in getting to where you are now?
Well, I was born in KwaZulu-Natal, near Ulundi, in Mahlabathini. Okay. And then my parents were working in Johannesburg. And then but I stayed a little bit in Mahlabathini and then went to stay with my parents in Johannesburg. And then later on, they took us to Swaziland to study. So that's where I did my first degree. And then when I came back, then I was able to do my master's and then my PhD all at UKZN.
Okay, and that's great. I also did my PhD at UKZN, so we have that in common. Now, Prof. Kunene, in the middle of the booklet, there's a lot of information about all the different science degrees that are available in the Faculty of Science and Agriculture, which you lead at Unizulu. So why would you encourage these matric science students to come and study at Unizulu?
The Faculty of Science and Agriculture is really strong in science and especially research, you know, so, and also we have these collaborations, especially internationally. So most of our students, they go out for an exchange. We've got collaborations with Chile, we've got Italy, we've got Russia, all these important institutions for research. Our students, they go there to do some kind of learning experience just to get more exposure. And also, we've got very good experts in their field, the supervisors. So, and for example, we've got two of our students, however, they did MSc and then they went and did PhD elsewhere in biochemistry, and they are working in the research for Prof. Karim Abdul Karim. They are working with him in the COVID research. We've got a lot of many other graduates that are really having an impact in the country that come from the Faculty of Science and Agriculture.
That's fantastic. Thank you. Those are all good reasons to study at Unizulu. Now, of course, before they can come and study at Unizulu, the students have to first complete their matric. And 2020 has been a challenging year. So can you perhaps just give a word of encouragement to our current matric students?
Yes, and the most important thing is that the COVID-19 has changed everything. So, for them, I would encourage them not to give up, not to keep dwelling on the past, to say this is how we were learning, this is how we were doing things, and so perhaps moving forward, then we can't do anything. No, they have to adapt to the situation and move on and adapt to the kind of learning that they have to do right now in order for them to be successful. So dwelling in the past on how we were doing things is not working and it's not going to work. So it's just moving forward.
Well, that's really good advice for any future, is always to move forward. Thank you so much, Professor Kunene, the Dean of the Faculty of Science and Agriculture at the University of Zululand.